Hey there, this is Lucius Laframboise from ENG Suite, and today we're going to continue talking about ANOVA post hoc testing. So you might notice that we've been talking about this a lot lately, and that's because we're closing up our ANOVA series with, okay, we did an ANOVA, now what? And so when you do a one-way ANOVA, you might see results that show you that one or more of your treatment levels does have a significant effect. So that means that we need to perform further testing, post hoc testing, after event testing, to determine which of those treatments are significant. And last time, we learned how to use the Fisher LSD method to take a look at direct comparisons of pair groupings. And this time we're going to use the Tukey Pairwise Comparison to actually group the treatments. And this, to me, is a really great way to see how they group. Not necessarily individual comparisons of groups. Even though it's called the Tukey Pairwise, this one does not actually show you the pairwise comparison, but it does perform a pairwise comparison, and we'll see that in a little bit. Okay, so how do we read our Tukey comparison table? So you'll see here we have it broken down by all treatments, but they're not necessarily in the treatment order that we provided them. They're actually in decreasing mean order because that's how the comparison is done. You'll notice that's a common theme in these post hoc tests. This time, we're not using our confidence interval. So remember, this is the same data. This is actually the same data that we used in way back in our ANOVA one-way video, and in our confidence interval table, and in our Fisher LSD table. And so because of our ANOVA, we did see that one of the treatments had a significant effect. But if we look at these confidence intervals, they all overlap with all of them. They're all overlapping, which if we use the confidence intervals, we would say, well, there's no significance. So we're not using our confidence interval. This time, we're using this grouping column. And the treatments with the same grouping letters are not significantly different. So as we saw in our Fisher and our confidence intervals, treatments 3, 2, and 4 were not significantly different from each other. They're all in group B, whereas group A, treatment 1, was significant from the rest. So that's how you tell. If they share a letter, they are grouped. But what if there's multiple groups for one treatment? So like treatment 3 here, we have A and B. So in this example, treatment 3 is part of group A and B. And that means that there's no significant difference between the treatments in group A and the treatments in group B. But some groups in A and B are significantly different. So that means everything in group A, treatment 1 and 3, are not significantly different. Everything in B, treatments 3, 2, and 4, are not significantly different. But treatment 1 is in A, treatment 2 and 4 are in B. There's no overlap in the groups. That means they are significantly different. So this is actually almost the same data. We just changed one number, and because we have so few samples, which is not appropriate, this is just a learning experience, we were able to move our treatment 3 mean up slightly enough so that it's now part of both groups. So that is how the grouping works. If they share a letter, they're not significantly different. If they don't, they are. Okay, but how does the grouping work? So again, Tukey Pairwise does not use confidence intervals to group our treatments. Instead, significance is assessed for each pair combination using a t-critical value, and they are significantly different if the difference of means is greater than the t-critical. So again, this is really more of a summary of the Tukey Pairwise comparison. Okay, so if the difference in these two means is greater than the t-critical value, they are significantly different. We'll see that in just a sec. So the math behind the Tukey comparison, not incredibly complex, but it relies on some pretty big things. So one, you need your mean squared error again for this t-value. That's going to be in your one-way ANOVA. It's not that hard to calculate, but for our examples, for our purposes, we are going to use the QE Suite function QE.ANOVA one-way. Then this Q prime here, this is our studentized range distribution for the number of groups and degrees of freedom error. Again, DF error. This is, heavily relies on the fact that there is a one-way ANOVA involved. Okay, so here we take a look at this Q prime. That comes from a giant chart of values. We have that already in Excel for you. You're not going to want to copy and paste that. You're going to want to download that, but we'll get into it in a sec. Okay, confidence intervals, Super easy, actually. It's just your mean of the group plus or minus your T critical for that group. And as you can see, something I always like to point out is for the example that we're doing, we have a balanced ANOVA. The number of samples in each treatment group are identical, so we are going to see the same T values, the same width for our confidence intervals. Not always the case. If you have an unbalanced ANOVA and these are different N values, you will get different values. So don't, just be careful of that when you are doing this by hand. Okay, so grouping. Here's the procedure. And this will make more sense in a minute when we get into Excel and we actually do the grouping. So we're going to sort each treatment table by decreasing treatment means. Again, sort it by decreasing. Then we'll assign a letter to each treatment based on its order. So the first treatment, the largest mean is going to be A, the second is going to be B, all the way down as many treatments as you have. And for each treatment, we're going to compare the difference of its mean to the next sequential mean in the decreasing order to the current mean's critical T. Again, that's where that if the difference of means is less than the critical T. But the critical T that you're using is always of the higher mean group because we're always assessing based on the higher mean. So if the difference is less than that critical value, then they are grouped together in that group. So let's take a look in Excel. Here is a summary here for you, but let's take a look at all of this math in Excel. So again, we're in that same workbook we've been working on since our one-way ANOVA. Go ahead, download this link in the description. It's going to be super duper helpful when it comes to learning all this. It's going to have the math in it. You will need a QE Suite free trial. Go ahead and get started. There's a link in the description that will show you how to do that. Otherwise, just downloading this workbook, Excel will prompt you to install QE Suite. Go ahead, install it, and that's going to automatically start your free trial for 2 months, and then you can do this along with me and use all the other great functions. Okay, let's get started. So first we're going to start in this unsorted table, and we're going to do what we love to do here, and we're going to just transpose our treatments. Okay, now what we want to do is we want to get our N value for each of those. So we're going to say count, and we're going to use our filter function, and we're going to select this entire array, and then we're going to select our treatment grouping array, and we're going to F4 to absolute reference, and then select the treatment name, and make sure you go back and absolute reference the array that we're filtering. And there we go. Now we can double click and they're all 5 just as we hoped. I'm going to copy this and then I'm going to paste it right here in the mean and just swap out that count function for average and double click. Okay, awesome. That was pretty easy, especially with those filter functions. Now it's time to move on to our T value, which means it's time to get our Q prime. Okay, so Q prime depends on 2 things, DF and our number of treatments. Let's start with our number of treatment groups. You know what? Let's go over here first. Let's get our degrees of freedom. So what we're going to do is we're going to do QE.ANOVA one way and select our entire thing with our treatment names. And there we go, one way ANOVA already done. P-value less than 0.05, which was our critical. We need to do a Tukey pairwise. So for our NT, let's just use the number of levels that we have because that's exactly what we need. DFE, we come down to our ANOVA table, DFE, enter. Okay, so now let's take a look at the studentized range distribution. You want to type all that out? Me either. Okay, we need to use our degrees of freedom and our number of trials. So these represent our degrees of freedom, these represent our number of treatments, and we are going to manually, no, I'm just kidding, we don't do that. We're going to use the index function. So index, and we are going to take the entire range of values. Do not take your index notices there. Okay, so row number. Row number is our degrees of freedom here, see? So now we're going to select DF right below there. So index in Excel is a function that is 1 based. So if we put a 1 in, we're going to get the first row, which is this. So that's awesome because if we put in 16, we're going to get the 16th row, which is exactly what we want. Now for column number, we take our NT. But as we see here, we start at 3. So now we need to make it so that if we were to put in a 3, we would get 1. So how do we do that? Well, we say 3 equals x minus 1. So we take our nt minus 2. And there we go. There is our q prime value. Let's double check. So we say 16, and that's 3. 16 with 4 treatments is 4.046. Sweet. Okay, so now we want our t value, which equals q prime, we'll absolute reference that, times the square root of, and then we're going to take our mean squared for error out of our ANOVA table, and then F4 to absolute reference over that n for treatment 1, enter, awesome, and again, remember, they should all look the same because n is the same, q prime and MSE are constants. Okay, confidence interval, just take our mean minus our t. Drop that down. Awesome. Now we're going to take our mean plus our t and drop that down. Awesome. What I want to do here is I want to come in here and I want to sort by that entire array by the means. Okay. Then I'm going to go in descending order. There we have our results. So it looks exactly like we recognize. We just have to come up with the groups, and we'll enter our groups in here. So as you can see down here, we have our comparison of each of these groups, and they're all sorted by, this was already in there for you, don't worry about it. So our mean difference, and here we're just going to take, this is treatment 1 and 3. So we're going to kind of do what we did earlier, where we're going to absolute reference that minus the next one. And then we can drop it down 3. Then we can come up, take the next group, absolute reference minus the following. And then drop that down. And then we can take absolute reference that. Actually, we don't have to. Just do that. Okay, awesome. So we have our mean differences for each of the groups. And then our t. Remember, we're taking the t from that higher treatment group. So we're going to take that. Let's absolute reference it. That way we can just drag that down. And again, they're all the same for this particular example, but I'm showing you how to do this, assuming that maybe you don't have a balanced ANOVA. And then we'll take treatment 2. Okay, so as you can see, we're only doing groups A for treatment 1, B for treatment 3, and C for treatment 2. We're not doing D for treatment 4. And that's because we don't need to in this scenario, because no matter what, it's going to be D. It's automatically. So something you'll notice is treatment 1 and 4 are automatically in groups A and D, just like these are automatically in groups B and C. And then I'll show you how to filter out those non-exclusive groups, I'll say. Okay, so grouped together. This is where we actually decide if these are grouped. So what we're going to do is we're going to say, is our mean difference greater than our t? And one quick thing I forgot is I actually need to pull this data here. So yours is going to look like this. In our, oops, not Fisher, we are doing the Tukey. Paste that. So that just kind of changed things up together a little bit in a lot of ways. But the reason I wanted to change that is I'm going to show you, this is the data that we originally started with in our one-way ANOVA. I'm going to show you what happens if there's multiple groupings. Okay, so we have that if that is greater. So actually, I want to make sure that we're thinking about this the right way. So if the difference is less than the critical value, then they're grouped together. So I said greater than. I just want to flip that. So if our mean difference is less than t, they're grouped together, because I wrote grouped together there. Okay, double click. Okay, so here we go. Treatment 1. So here's what we'll do. Is treatment 3 part of group A? So treatment 3 is here. No, it is not. What about treatment 2? Is treatment 2, and actually that would be C and B. Sorry about that. Nope. Is treatment 4? Nope, they are not. Okay. Treatment, so now we're looking at B. Is treatment 3 and 2, are they in group B? Yes. So treatment 2 is going to be a part of group B. Awesome. Treatment 4. Yes, treatment 4 is a part of group B. Okay, treatment 2 and 4. Is treatment 4 part of group C? Yes, it is. Okay, now you'll see that B is in all of these three. C is in B group. There's no difference. C does not is not a unique group from B, so we'll get rid of B. We see here D is treatment 4. It is also not a unique group. So now we have A, B, B, B. All right, let's do this, and let's say QE dot, and we're doing the Tukey pairwise. We put in our entire treatments, and there we go. And we see we have treatment 1, 3, 2, 4, A, B, B, B. Okay, like I said, let's see an example where we should actually have two groups that overlap a little bit. So if we change that 2 there to a 3, we see all of a sudden QE Suite redoes it and says, okay, treatment 1 and 3 are part of group A, but treatment 3 is also in group B with 2 and 4. So let's take a look at why that might be. So all of the math stays the same. The only difference is our pairwise comparisons. Because now something might shift is the order, but we didn't adjust our mean quite that much. Okay, here we go. It's treatment 1 and 3 part of group A. Yes. So here, let's go back in here. We say A, C, B, D. That's our standard grouping, right? They're automatically in their own groups. Okay, treatment 3. Is that part of group A? Yes, it is. Because we have that true. It is greater. It is less than 3.04. Okay. Treatment 1 and 2. No, treatment 2 is not part of group A. Neither is treatment 4. Okay. Treatment 3 and 2. Is treatment 2 part of group B? True. So treatment 2 is part of group B. What about treatment 4? True. Treatment 4 is in D and B. Now, treatment 2 and 4? Yes, treatment 4 is part of group C. Okay, so now you'll see C is only in group B. So we can get rid of that. And that'll make a little more sense when we take a look at this. So I'm going to reorder this. I'm going to say it's part of B and D. And we see, yeah, actually, B and A are distinct groups because group B contains treatments 2, 3, and 4, right? And actually, group D is not a unique group, but group B doesn't include treatment 1. So it is unique from group A, which includes treatment 1 and treatment 3. So because they take different, it's sort of like a Venn diagram. It does not have they are unique groups because they have different combinations without omitting any that are in other groups. And as you can see, let's just change this to A, B, put it in order, and yes, we see we have the exact same results as QE Suite. So that's your Tukey pairwise comparison. That's your grouping. That's how it works. Super cool. Thank you so much for watching. Have a great day, and please do something awesome.